Hello everybody, welcome to take 2 of my pulleys video. So I have posted a pulleys video in the past going through those types of force problems, and I've gotten some feedback from students and realized that I don't explain them as clearly as I could, so I wanted to go ahead and film a new version of this video that hopefully does a better job of explaining what it is I'm trying to get across. So the biggest thing with pulleys, so they're just the concepts and the equations that you're going to be using are just going to be the force equations, but now you have these objects arranged in such a way that one could be moving along a totally different axis than the other, but because they're connected by this string, then they share the magnitude of their acceleration, even though one could be, if you have a block sitting on a surface and then one hanging off the edge of that surface, one of them is moving in the y and one of them is moving in the x. But that size of A is the same. So the biggest issue is typically just being careful about using your signs when doing the problem. Depending on if you're comfortable, and I'm going to go through and explain it in the example because I think that that's the easiest way to show you both sides simultaneously. But essentially, you can either think of solving these problems using your traditional XY axes and those sign conventions, so that down is always negative, up is always positive, and the usual convention for X. Or you could think about it in terms of the whole system or the objects connected by the rope being a system, and have the positive be moving along the motion axis, so following the motion of the whole object and having that direction be positive and the opposite direction be negative. And there's some advantages to using that way, but it is a little bit more complicated and it's not necessary. So I just want to offer it as a possible option for those of you that it clicks with, and if it doesn't, then just go ahead and use the normal stuff. It works just as well. And yeah, so I think that that's all I have to say. Sorry about the confusion if you watched the last video and didn't really understand the point. Please continue to give me feedback if things are confusing, and I'm happy to go back in and clarify and make edits if I need to. This is all about understanding the material. So yeah, without further ado, let's go revisit pulleys and hopefully get it right this time.
Two masses, 1 kilogram and 2 kilogram, are connected by a string over a pulley. What is the acceleration shared by the two masses? What is the tension in the string? I'm first going to draw a picture, but I will say I am going to be solving this problem two different ways. And there's just kind of two different ways that we can think about the axes and what we typically call positive and negative, and that's going to be really important when solving these problems because with pulleys, there is often probably the most common mistake is going to be a sign mistake, but it changes the number, the numerical answer you get drastically. So I'm going to show two different ways. Pick the way that makes the most sense to you. You'll get the same answer either way. I just want to show both because for some people, one way makes a lot of sense, and for other people, the other way makes a lot of sense. I don't have a name for them, so I guess I'll just call one of them normal, um, which it typically is the normal way we think of up as always being positive and down as always being negative. We'll do normal, sign convention, and then we'll do I guess I'll call it motion axis sign convention. So the picture we're going to have is we have our pulley, we'll have M1 and M2. So this is 1 and this is 2, and then I'll go ahead and copy this and put it over here so that we have both. So for our normal sign convention, I'm going to write the axes in this light blue. We're going to have down being negative, up being positive, and that's just tried and true. That's always the way it is. On the other hand, the other way that we could think about this is that basically this guy is going to be moving in such a way that if 2 moves down, and I'm just going to keep drawing downward arrows, the whole system, so both masses and the string, are going to be moving this way, which means that one mass, the acceleration is going to be positive, and one mass, the acceleration is going to be negative in our normal sign convention. But what you can do instead is you can think about the axes as being positive and negative, as in positive going along with the motion and negative being in the opposite direction of motion, which would mean that down is positive on the right-hand side, and that means down is negative or up is positive on the left-hand side. And I'm going to end up erasing most of these, but I just want to kind of show you how that sign convention carries. But I'll write that this negative, positive, negative, and then erase all these little guys. And otherwise, everything else is going to be the same. So we're going to go ahead and draw our forces. So we'll have, I'll call FG1 and force tension on block 1. We'll have FG2 and force tension for block 2. And then I'm going to go ahead and just also draw, and this isn't something that for every problem you're going to know right off the bat, but since we have just vertical forces, just tension and gravity here, we know from intuition that the 2 kilogram mass is going to be the one that is going to be falling towards the ground, and the 1 kilogram mass is going to be the one moving upwards toward the pulley. So we know that our acceleration will be going down for the bigger one and up for the smaller one. And we'll do all the same things on this side, right? So we'll still have our forces. Everything's going to be the same picture-wise. The signs are going to come into play when we actually plug into our F-net equation. And we'll still have A and A. So for normal sign convention, we're going to write out the sum of the forces. Well, I'll put mass 1 and mass 2. So the sum of our forces in the y equals mass 1 times A. The sum of the forces in the y equals mass 2 times negative A. So we need to put that negative sign in there. And then based on our normal sign convention, we'll go ahead and put in Ft minus Fg1 equals M1A, and Ft minus Fg2 equals negative M2A. So just pulling that negative sign out of there. Okay, now for doing the exact same thing with the different sign convention, let me write these headers. Sum of the forces in the y equals M1A. Sum of the forces in the y equals M2A. Now we have, so mass 1 is all pretty much the same. We're going to have Ft positive minus Fg1 equals M1A. But for mass 2, now our positive direction is down, so we're going to have plus Fg2 minus force tension, since now upwards is negative, equals M2A. So, and if we just take a peek for a second, if I were to take say the mass 2 F net equation from the normal sign convention and multiply both sides by a -1, then this would become minus Ft plus Fg2 equals M2A, which again, if you make one more substitution, so just switch the order of those forces being added to each other, then you end up, it's the same exact equation. So the only difference is that one of them has a negative sign multiplying both sides and one of them doesn't, but they are the same exact equation. So it's really just going to become a matter of which sign convention you like more. Otherwise, all the other steps are going to be, like I said, exactly the same. So with that being said, I'm going to go ahead and stick with, do I fill these back in, the normal sign convention, and we're going to go ahead and solve this for, oh, nope, I lied. There's one other F net equation that we can write out here. That's important. So you might be asking me, Curran, why would you even show us this motion axis sign convention? It's kind of confusing and ends up giving us the same equation as long as we're careful with signs with the normal sign convention. And there's really only one big advantage I've seen to using this motion axis sign convention, and it comes from if you're only asked to solve for acceleration, then we can think about the blocks and the string as being an entire system, so being one whole object since they're all connected and they're all going to be moving at the same acceleration instead of looking at the blocks individually. And then this would allow us for any internal forces to basically disappear because then the tension becomes a force within the object itself, and we don't care about those. We only care about external forces. But we can't do this with normal sign convention because we'll end up getting the wrong sign on the forces. So I'm not even going to bother writing them out, and I'm only going to write this on the motion axis sign convention side, is that we can look at the system instead of the individual blocks. And if we do that, we'll say the sum of the forces in the y equals the total mass of the system, so this will be m1 plus m2 times the acceleration. And then from our motion axis sign convention, we'll have Fg2 minus Fg1 equals m1 plus m2 times a. Okay, so now that I've gone through all of this, let's solve for acceleration. First, I'm going to just solve it. I'm going to get it to a point where you can see that the equation you get is going to end up being the same as the one you would get from the system, but it's a lot longer to find. So since we're interested in solving for acceleration, we want to get rid of our tension from our two equations, and we're also going to use the normal sign convention side. I guess I'm going to use the equations for mass 1 to get an expression for Ft. So we're going to add that Fg1 to both sides. We'll get Ft equals m1a plus Fg1, and then that is going to be substituted into the mass 2 equation for Ft. So m1a plus Fg1 minus Fg2 equals negative m2a. We'll combine the a terms together by subtracting, and that gives us Fg1 minus Fg2 equals negative m2, negative m1a. And if we pull out a negative a, times m1 plus m2, and then multiply each side by a negative sign, that negative sign is going to distribute by giving us negative FG1 plus FG2 equals A times M1 plus M2, which you can see hopefully is exactly the same as what we got from the system. But we can go ahead and substitute in that this will be negative M1G plus M2G equals A plus M1 plus M2. We'll divide both sides by M1 plus M2 to get A by itself, and then we could also pull out a G if we want from the top, so I'll do that. So G minus M1 plus M2 over M1 plus M2 equals A. So 9.8 negative 1 plus 2 over 1 plus 2 equals 3.23, or 27, sorry. The second part of our question is asking for the tension. So now that we have acceleration, we can just plug that into the equation that we had for box 1 and then solve for Ft. So I'll squeeze this in here. Ft is going to be 1 times 3.27 plus 1 times 9.8. Which equals 13.1 newtons. Okay, and as promised in the incline planes video, here's our pulley and incline plane combo problem. If you haven't watched that one yet and you're confused about the force diagram I draw, go ahead and just re-watch or watch that first before going through this example. But if not, let's get into it. So we're going to solve for the coefficient of static friction needed to keep this system stationary. I'm pretty sure I am going to need masses, so I'll just make up the same ones. So obviously my drawing skills are not the best, so not drawn to scale, but we'll just make them both M. So same mass. Easy peasy. Okay, and we're solving for mu s, so let's draw our forces. Well, we've got Fg, we've got normal, and I guess I should call this Fg1. I'm not going to call it normal 1 since the second guy doesn't have a normal force. Fg. I'll do, since in the other video I did parallel and perpendicular the whole time, I'll do y and x. This also leads us to having positive being down the ramp, negative being up the ramp, and if we carry that over here, then it would be negative up and positive down. And then I'll just call it FGX and FGY because I don't want to carry around a million labels. And the second mass is only going to have one gravity component. So Fg2, and then we have tension, and then here's part of the dilemma, is that we don't know which direction this system wants to move. So we don't know exactly which way to draw friction, and that makes a difference. So first thing I would say to do something like that is you need to treat, what I think the fastest thing to do is to treat this as a system and see what direction acceleration would come to without friction being present, and then friction has to go in the opposite direction of that. So let me show you what I mean. So we're going to say, so first we're going to pretend no friction to see direction of A. So we'll have FG2. Did I do this? I did this wrong. Oh my gosh. My apologies. If we carry that along, this should be negative and this should be positive. Okay, so then we're going to have a positive FGX minus FG2 equals total mass, so M plus M times A. Our FGX is equal to FG1 times sine theta. This also comes from the inclined plane video, so I'm just going to write them out. We're going to substitute the x1, sine theta minus FG2. So I'm going to consolidate that into 2MA. We can put in mg sine theta minus mg equals 2MA. We actually get masses canceling out by making them equal, so that's nice. And then, oh, I didn't give this an angle. Make it 30 for easy math. 10 sine 30 minus 10 equals 2a. So sine of 30 is a half, so that'll become 5 minus 10 equals 2a. And from this, well, that'll be a negative 5 equals 2a. That tells us that a is actually going to be moving this way. So our theoretical A is moving in the negative direction, which means our friction needs to point in the positive direction. So now I'm going to go ahead and add. So A negative, FS positive, which means it'll be pointing this way. Okay. So now we've done that, we can go ahead and solve for what we're interested in. So let's first do individuals, I guess I'll call it, and then we'll do a systematic outlook afterwards. So we'll have first guy and the second guy. For the first one, we're going to have sum of the forces in x equals 0, where we'll have FGX plus static friction minus tension equals 0. If we expand that and just put mu s times Fn minus t equals 0, we need normal force. So we'll get that from taking the sum of the y. Sum of forces in the y equals 0. We'll get F normal minus FGY equals 0. So if we add that over, we'll get that F normal equals FGY. So I'll make that substitution. This one's the next still. FGY minus tension equals 0. That's as far as we can go there, so I'm going to leave it. And then we'll look for sum of the forces for box 2, which will be tension minus FG2 equals 0. So for both of these, or for this one, I'm going to go ahead and add tension over to the other side, so that way we can get an expression for tension. I did not leave myself a great amount of room, so I'll put that over here. FGX plus mu s FGY equals tension, and then all of this is going to go in for tension. So then we'll have FGX plus mu s FGY minus FG2 equals 0. Now we're solving for mu s, so I'm going to subtract FGX and add FG2 to both sides. I don't have the space, so I'm going to write them there and then just rewrite on the next line the outcome. So we'll have FG2 minus FGX, and then we can divide out this FGY. In the next step, we'll go ahead and plug in what these guys are. So FG2 is just going to be mg. FGX is going to be mg sine theta. So substituting in first this, and then that mg equals fg. And then for y, it's mg cosine theta. So we got a lot of cancellations. So each term has an mg in it, so we can cancel both those out. And we'll be left with mu s is minus 1 sine 30 over cosine 30. And this is going to be equal to 0.578. Probably only need 2 sig figs actually. And I rounded that wrong. My bad. That'll be equal to 0.58. But if instead we do a system, I'm just going to show that you end up with that same equation that we just had. So we'll have FGX plus FS minus FG2 equals 0. So I'm going to make the same substitutions as I did before. mg sine theta plus mg cosine theta. Oh, that should have a mu s in front of it. That's what we're solving for. Minus mg equals 0. And if we go ahead and rearrange all this, I mean at this stage, it's hard to tell, but even at this stage, you can see that this equation is the same as this equation if you squint and make it out. So I'm not going to go ahead and follow through with the math. The math will all be the same, and you should get the same number. So where are you?
Say bye to the kiddos. Good boy.